Welcome to Week 6 Summary for the online course Fundamentals of Electronic Materials and Devices. In this week, we will look at transistors. The vacuum tube diode and triode are essentially the forerunner for the modern day PN junctions and transistors. A diode is a two-terminal device. Basically, we have an anode and a cathode. It allows current to flow in one direction but not in the other. So thus a diode is a rectifier, and we have already seen the solid state equivalent of it, which is the PN junction. In this week, we will look at the transistor, which is the solid state version of the triode. The triode is a three-terminal device, so there is an anode and a cathode, but in addition, there is also a grid which is independently controlled from the anode and the cathode. The triode or the transistor can be used as either an amplifier or as a switch. There are essentially three types of transistors. The first one we are going to talk about is called the bipolar junction transistor, or BJT. It is a current control device and it has three distinct regions called the emitter, base and the collector. Two configurations are possible. We can either have an NPN, in which case the emitter and collector are N-type, the base is P-type, or we can have a PNP, which is just the reverse. The transistor has two PN junctions, so there is a junction between the emitter and the base, and similarly there is a junction between the base and the collector, and it has three terminals linking the emitter, the base and the collector. There are three configurations in which a BJT is operated. It can either be a common base, common emitter, or a common collector. So depending on how the BJT is operated, it can be used for power gain. So if we have a common base mode, when the voltage at the base collector is greater than the voltage for the base emitter junction, then the collector power is greater than the emitter power, and we can use it for power gain. When we use the BJT in a common emitter mode, it essentially acts as an amplifier because the base current is the signal that we supply, and it is in turn amplified by the collector. For a bipolar junction transistor, we normally say that the emitter current is equal to the collector current plus the base current. One way to think about it is, let us say I have an NPN BJT. When electrons flow from the emitter through the narrow base, some of it gets recombined, that forms the base current, and the remaining electrons go into the collector region, which is why IE equal to IC plus IB. We also define a gain, which is nothing but IC, which is the collector current, divided by the emitter current. The next type of transistor that we are going to talk about is a voltage control device, which is called a junction field effect transistor, or JFET. So once again, we have three terminals. We have a source, we have a drain, and we have a gate. We also have a channel through which carriers flow from the source to the drain. In the case of a JFET, the channel already exists when the device is fabricated. So in this particular case, we have a source which is N-type, and basically we have two regions which are essentially heavily doped P-type. So this in turn lets us form two junctions between the P plus and N, and we have a depletion region which is formed in the N-type region. Between the two depletion regions, there is a narrow channel in which electrons can flow, and this is called the N channel. So this figure is just a two-dimensional cross-section showing the N channel from which electrons can flow from the source to the drain. The width of the channel is controlled by the voltage that is applied to the gate. So essentially, this is an example of a voltage control device. Now, when the gate is shortened out, so basically when there is no potential applied to the gate, we apply a positive potential to the drain, so electrons can flow from the source to the drain. However, applying a positive potential essentially means that this drain and gate is reverse biased, and so the channel tends to narrow off. And as we keep on increasing the drain voltage, uh, at some particular point, pinch off occurs, and then the current is essentially a maximum. We reach saturation. So drain is biased positive, and electrons flow from the source to drain, and pinch off occurs at high voltage. Now, instead of shorting out the gate, if I apply a negative voltage to the gate, we basically reduce the width of the channel, which means that the drain current is also reduced. So this is an example of the voltage of the drain current as a function of the drain source voltage. So initially when the gate is shorted, the current increases and then gets saturated. However, when I apply a negative potential at the gate, I am reducing the width of the channel, which means the current also reduces, and so the IDS value reduces. As VGS becomes more negative, at one particular point, the channel is destroyed and we have zero drain current. So a JFET is an example where applying a voltage to the gate basically reduces the current in the channel, and that it controls the flow of current from the source to the drain. Another example of a voltage control device is called a MOSFET, which is a metal oxide semiconductor field effect transistor. So once again, we have a source, a drain, and a gate. But the important difference between the MOSFET and the JFET is that the channel is created only during device operation. So there is no channel when there is no voltage, unlike the JFET where a channel already exists in the transistor. We can have two types of MOSFETs, either an NPN with an N channel or a PNP with a P channel. So once again, we can look at how the MOSFET works. When there is no voltage applied to the gate, there is no channel, which means current cannot flow from source to drain. There is essentially no current. When we now bias the gate, so this is an NPN, so when we bias the gate positive, we essentially drive electrons towards the gate so that we create an N channel for the electrons to flow from the source to the drain. For a given gate voltage, as the voltage at the drain increases, the current increases until we have pinch off, and basically the current gets saturated. If we keep on increasing the gate voltage, the channel width increases so that the current also increases, of course, until we reach saturation. In this way, the behavior of the MOSFET is opposite to JFET, where the application of the voltage to the gate destroys the channel. Here, the application of the gate voltage actually increases the channel width. We can look at how the channel is created in the MOSFET by focusing only on the metal oxide semiconductor path. We know that if I have a metal and a semiconductor, I can sort of think of setting up a capacitor kind of system. So in this particular example, we have a p-type semiconductor and we have a metal. The metal is biased positive, which means positively charged ions are found at the surface of the metal. So we have a net positive charge in the metal surface. Correspondingly, when I connect the p-type semiconductor to negative, remember, holes are the majority charge carriers here. These holes tend to go towards the negative side, and all of the electrons tend to accumulate at the surface of the p-type semiconductor. Eventually, when the voltage is high enough, we basically have initially we have a depletion region, and as the voltage increases, we finally have an inversion region at the surface of the p-type semiconductor where we have more electrons than holes. This inversion region is nothing but the N-channel that is created in the MOSFET. We can look at the band structure of the MOSFET. For simplicity, we choose an N-type material whose Fermi level lines up with the Fermi level of the metal so that it is easier for us to understand the creation of the channel. So we have both examples here, both the creation of a p-type channel and the creation of an n-type channel. When we now apply a bias, depending upon how the bias is applied, we can either have accumulation of carriers or we can have depletion. Accumulation of carriers is not good as far as creating the MOSFET goes, so that is not something we will talk about. When we apply the potential in such a way that we have depletion, we basically have the minority carriers essentially accumulate at the surface of the semiconductor. Ultimately, as we keep on increasing the voltage, we have a regime where we have excess electrons at the surface. In the case of a p-type semiconductor, so this is your n channel, or we have excess holes at the surface. In the case of an n-type semiconductor, so this is your p channel. So an inversion regime is what we want as far as a MOSFET is concerned. So we can then now try to understand the formation of the MOSFET just based upon how much the bands are bent. We can define a bulk potential, which is nothing but the difference in the intrinsic Fermi level minus the Fermi level of your starting semiconductor. So in this particular example, it's a p-type semiconductor. The bulk potential essentially depends upon the dopant concentration in the semiconductor. When we now apply a potential such that we drive the minority carriers to the surface, we can define a surface potential, which is nothing but how much the bands have bent, and this is EFI at the surface minus EFI at the bulk. So remember again, this is a p-type semiconductor and we are pushing electrons to the surface in order to create an n-channel. The extra electrons that are available at the surface is equal to the difference between the surface potential and the bulk potential. We can also calculate something called the channel width. The channel width again depends upon how much surface potential that we apply. There is a particular case of inversion, which we call strong inversion, when the surface concentration of electrons is equal to the bulk concentration of holes. We describe this as a particular scenario when the surface is as strongly n-type as the bulk is p-type. So when this strong inversion happens, the surface potential is 2 times the bulk potential, which is equal to 2 kT ln of Na, which is the acceptor concentration, divided by Ni. When I plug in this phi s into this equation, I can calculate the total channel width under strong inversion, and we can also calculate the width of the depletion region, the width of the n channel when we have strong inversion. Wm here is the total width of the depletion region. So this channel which we create under strong inversion is what is used to carry the electrons from the source to the drain. So in this week, we have looked at 3 types of transistors: a current control device, which is nothing but the bipolar junction transistor, and 2 voltage control devices. One is the JFET, the other is the MOSFET. And we've also looked at creation of the channel in the MOSFET by focusing only on the metal, oxide, and semiconductor region. With this, we are done with week 6. In the remaining 2 weeks, 7 and 8, we will look at the interaction of light with semiconductors and from there we will transition on to optoelectronic devices. Thank you.